Hello everyone, welcome to today's session. Today we'll work on the practical part of decision tree. Before we drill down to a practical session, a common question might come to your mind. You might think that our tree-based model is better than the linear model. You can think about using logistic regression for classification problems and linear regression for regression problems. Then why is there a need to use a tree? Well, many of us have this in their mind, and there's a valid question too. Actually, as I said earlier, you can use any algorithm. It depends on the type of problem you're solving. Let's look at some key factors which will help you to decide which algorithm to choose and when. So, the first point being if the relationship between dependent and independent variables is well approximated by a linear model, then linear regression will outperform tree-based model. The second case, if there is a high non-linearity and complex relationship between dependent and independent variable in a tree model will outperform a classical regression model. In the third case, if you need to build a model which is easy to explain to people, a decision tree model will always do better than a linear model, as the decision tree model are simpler to interpret the linear regression. Now let's move on ahead and see how you can write a decision classifier from scratch in Python using the CART algorithm. For this, I will be using a Jupyter notebook with Python 3.0. Install on it. So let's open the Anaconda and the Jupyter notebook. So this is the Anaconda navigator, and I will directly jump over to the Jupyter notebook and hit the launch button. I guess everyone knows that Jupyter notebook is a web-based interactive computing notebook environment where you can run your Python code. So my Jupyter notebook is open on my localhost 8889. So I will be using this Jupyter notebook in order to write my decision tree classifier using Python. For this decision tree classifier, I have already written set of codes. Let me explain to you just one by one. So we'll start by initializing our training dataset. So this is our sample dataset for which each row is an example. The last column is a label and the first two columns are the features. If you want, you can add some more features as an example for your practice. An interesting fact is that this dataset is designed in a way that the second and fifth examples have almost the same features, but they have different labels. So let's move on and see how the tree handles this case. As you can see here, both of them, the second and the fifth column, have the same features. What is different? Just their label. So let's move on ahead. So this is our training dataset. Next, we are adding some column labels. So they are used only to print the trees. So what we'll do is we'll add a header to the columns. Like the first column is of color, second is of diameter, and third is a label column. Next, what we'll do is define a function as unique values in which we'll pass the rows and the columns. So this function is what it will do. It will find the unique values for a column in the dataset. So this is an example for that. So what we are doing here, we are passing training data as our row and column number as 0. So what we are going to do, we are finding unique values in terms of color, and in this sense the row is training data and the column is 1. So what you are doing here, we are finding the unique value in terms of diameter. Fine. So this is just an example. Next, we'll define a function as class count and we'll pass zeros into it. So what it does, it counts the number of each type of example within the dataset. So in this function, what we are basically doing, we are counting the number of each type of example in the dataset. Or what we are doing, we are counting the unique values for the label in the dataset. As a sample, you can see here, we can pass that entire training dataset to this particular function as class underscore count. What it will do? It will find all the different types of labels within the training dataset. As you can see here, the unique label consists of mango grape and lemon. So next, we'll define a function that is numeric and will pass a value into it. So what does it do? We'll just test if the value is numeric or not, and it will return if the value is an integer or a float. For example, you can see it is numeric. We are passing 7, so it is an integer. So it will return in value, and if we are passing red, it's not a numeric value. So moving on ahead, where you define a class name as a quotient. So what this quotient does? It used to partition the dataset. This class, what it does? It just record a column number. For example, 0 for color and a column value, for example, green. Next, what we are doing is defining a match method which is used to compare the feature value in the example. The feature value stored in the quotient. Let's see. First of all, what you're doing, we're defining an init function, and inside that we are passing the self column and the value as a parameter. So next, we define a function to match. What it does? It compares the feature value in an example to the feature value in this quotient. When next, we'll define a function as rep, which is just a helper method to print the quotient in a readable format. Next, what we are doing is defining a function partition. Well, this function is used to partition the dataset. Each row in the data set check if it matches the quotient or not. If it does so, it adds it to a true rows, and if not, then it adds to the false rows. For example, as you can see, it's partitioning the training dataset based on whether the rows are right or not here. We are calling the function quotient and we are passing a value of 0 and reading it. So what did we do? It will assign all the red roses to true underscore rows, and everything else will be assigned to false underscore rows. Next, we'll define a Gini impurity function, and inside that we'll pass the list of rows. So it will just calculate the Gini impurity for list of rows. Next, we are defining a function as information gain. So what does this information gain function do? It calculates the information gain using the uncertainty of the starting node minus the weighted impurity of the child node. The next function is to find the best plate. Well, this function is used to find the best quotient to ask by iterating over every feature of value and then calculating the information gain. Next, we'll define a class as leaf for classifying the data. It holds a dictionary of class like mango for how many times it appears in the row from the training data that reaches the leaf. Next is the decision node. So this decision node, it will ask a quotient. This holds a reference to the quotient and the two child nodes on the basis that you are deciding which node to add further to which branch. So next, we're defining a function of a build tree, and inside that we are passing our number of rows. So this is the function that is used to build the tree. So initially what we did was define all the various functions that we'll be using in order to build a tree. So let's start by partitioning the dataset for each unique attribute. Then we'll calculate the information gain and then return the quotient that produces the highest gain, and on the basis of that we'll split the tree. So what we are doing here, we are partitioning the dataset, calculating the information gain, and then what this is returning, is returning the question that is producing the highest gain. Now if gain equals 0, return leaf rows. So what it will do? So if we are getting no for the gain, that is gain equals 0, then in that case, since no further question could be asked, so what it will do? It will return a leaf. Now true underscore rows or false underscore rows equal partition with rows and the question. So if we reach this position, then you have already found a feature of value which will be used to partition the dataset. Then what will you do? You will recursively build the true branch and similarly recursively build the false branch. So return division underscore node and side, that will be passing quotient on a true branch and false branch. So it will return a quotient node. This quotient node recalls the best feature or the value to ask at this point. Now that we have built a tree, next we'll define a print underscore tree function which will be used to print the tree. So finally, what we are doing in this particular function is that we are printing our tree. Next is the classify function which will use it to decide whether to follow a true branch or a false branch and then compare the feature values stored in the node to the example we are considering. And lastly, we'll finally print the production at the leaf. So let's execute and see. So there's our testing data. So we printed a leaf as well. Now that we have trained our algorithm on our training dataset. Now it's time to test it. So there's our testing dataset. And let's finally execute it and see what is the result. So this is the result you will get. So first question which is asked by the algorithm is diameter greater than equal to 3. If it is true, then it will further ask if the color is yellow again. If it is true, then it will predict mango as 1 and lemon as 1. And in case if it is false, then it will just predict the mango. Now this was a true part. Now the next coming to diameter is not greater than or equal to 3. Then in that case it's false. And what did we do? It just predict the grape. This was all about the coding part. Now let's conclude this session. But before concluding, let me just show you one more thing. There's a Sci-kit Learn algorithm cheat sheet which explains which algorithm you should use and when. Let's build in a decision tree format. Let's see how it is built. So first condition, it will check whether you have 50 samples or not. If your samples are greater than 50, then we'll move ahead, and if it is less than 50, then you need to collect more data. If your sample is greater than 50, then you have to decide whether you want to predict a category or not. If you want to predict a category, then further you will see whether you have label data or not. If you have label data, then that would be a classification algorithm problem. If you don't have the label data, then it would be a clustering problem. Now, if you don't want to the category, then what you want to predict a quantity. Well, if you want to predict a quantity, then in that case, it would be a regression problem. If you don't want to predict a quantity and you want to keep looking further, then in that case, you should go for dimensionality reduction problem. And still, if you don't want to look and the predicting structure is not working, then you have tough luck for that. I hope this decision tree session clarifies all your doubts over the decision tree algorithm. So this is all about the practical session on decision trees. In the next session, we will work on the random forest. Thank you so much, guys.